application of circular dynamics is the banking, or tilting, of a road along its curves. You've probably felt the effects of this type of motion before. When you are traveling in a vehicle and the vehicle makes a sharp right turn, you often feel like you are being thrown to the left. But are you? Think about that for a second. Is there a force that is pushing you in that direction? There's not. What happens is you are traveling along in the car in a straight line. Your inertia wants you to keep moving in that straight line. So when the car turns, you keep moving in your straight line while the car goes off to the side. In order for you to keep moving with the car, your seat or the door or something must exert a force on you to keep you moving with the car. So you feel like you're being thrown against the door, when in reality you're just continuing on your forward motion. The same kind of thing is happening to the car itself. The car's inertia wants it to keep moving in a straight line. On a flat road, the only thing that keeps the car moving through the turn is the friction between the tires and the road. So it is not uncommon for roads to be banked slightly or sloped to accommodate higher rates of speed. An ideally banked curve is one in which the angle is such that you can negotiate the curve at a given speed without needing friction to keep you on the road. This angle, still called theta, is measured with respect to the ground. For ideal banking on a curve, we want the net external force to equal the horizontal centripetal force in the absence of friction. So if your tires don't have any grip at all on the road, we don't want you to be flying off the curve. If the angle is ideal for the given speed of the vehicle and the radius of the curve, then the net external force will equal the centripetal force necessary to keep the car on the road. Remember, we're ignoring friction, so the only two external forces acting on the car are its weight, acting straight down, and the normal force acting perpendicular to the surface. So these two forces added together must give us a net force horizontal to the center of the curve and equal to the centripetal force. Now we know that the weight of the car acts only in the vertical direction. It does not have a horizontal component. Since the centripetal force acts in the horizontal direction, we can conclude that the weight doesn't even affect the centripetal force. Only the normal force has a horizontal component to it. That means that the centripetal force must be equal to the horizontal component of the normal force. Now the horizontal component of the normal force is the adjacent component to our angle theta, so we need to use the sine function to determine its magnitude. So n sine theta gives us the horizontal component of the normal force. And this is equal to our centripetal force. So if our object is moving in a circle on a surface that is at an angle to the horizontal, we use the horizontal component of the normal force in place of the centripetal force. Something else to keep in mind is that if the car does not leave the ground, then the vertical forces must be equal and opposite. The only force acting to pull the car down is the weight. This must be counteracted by the vertical component of the normal force, which is found using the cosine of angle theta. This gives us an expression we can use if we need to incorporate the vertical components into our calculations. Now what if we want to know the ideal angle of the banked curve? Since our expression for centripetal force and our expression for weight both involve the normal force in this situation, then we can combine them. Let's move a little bit more around and we can get our trig functions on the same side. This is handy because the sine of an angle divided by the cosine of an angle is equal to the tangent of an angle. We can also get rid of our term for mass at this point. If we really look at this expression, we can see that the angle of the banking, with no friction, really only depends on the velocity and the radius of the curve. The mass of the vehicle does not matter when you're determining how steep to bank a road. So the tighter the turn and the faster you travel, the more the road should be banked to keep you on it. So calculate the speed at which a 100-meter radius curve banked at 65 degrees should be driven if the road is frictionless. Based on what we just discussed, in order to find the velocity, if we know the radius and the angle, the best equation to use would be the tangent. We can rearrange to get velocity squared by itself and plug in our values. Square root both sides and we get a velocity of 45.8 meters per second.